just in case someone wants to watch an empty screen while I'm doing demonstration at some point. Okay, so welcome to General Physics 2. So this is typically like kind of the screen. This is not updated yet. Let me go back and see if this updates. Sync this notebook now. It's supposed to be the sun next to it too. One. Maybe this. Okay, I think it is. There's just more stuff on top. Okay, so chapter 22 is going to be on the electric charge, and I really like that the fact that the book does this, where I think a lot of other introductory physics books don't do this. They just jump straight into the electric force and not introduce you to, oh, what is a charge? How did the charge actually got discovered, and why do we see it, and why do we actually produce it at home if we just have a piece of plastic and a hat? Okay, and so the charge model is going to be fundamental to everything that we're going to be studying in this entire class, actually, where the electric charge is actually responsible for like 99% of all the phenomenon we experience every day. The thing that it usually doesn't include is gravity, which is a different force. And you guys in general physics have studied a little bit about gravity, but that's a slightly different bag of forces that you have to deal with. And then we're going to see how electric charges also creates its own force. And the fact that electric charge exists, allows you to, have electric cars, right? That makes sense, right? Your laptop, right, also runs on electricity. Anything that has electricity in it, right, basically runs on the fact that this phenomenon exists. If you ever seen, there was like a big lightning storm, maybe like 3 weeks ago over the winter break, right? You guys probably seen a bunch of lightning around. So lightning is also an electric effect, right? So that's just basically the clouds are getting charged as they move through the atmosphere. And we're gonna actually kind of see this on our little mini lightning rod out there. And the cloud discharges that charge onto the ground by having lightning traveling straight down from the cloud onto the ground. These are just electrons that are flying straight down to the, not straight, arcing through the atmosphere onto the ground. Okay. Sometimes we have geology majors in here. Do we have any geology majors this semester? No. The Earth is also a electromagnetic dynamo. The fact that we have a magnetic field around the Earth is because there's actually electricity and magnetism working inside the Earth to produce the magnetic field around us. So this little picture here might look a little bit abstract for those of you. Anyone can guess what this picture is supposed to show? Neurons, right? You guys are much smarter than me. Okay, so the human body, right, also works on electricity, right? The fact that I have a thought in my brain to move my finger, right? The fact that I can do this basically instantaneously is not because my brain released some chemical to tell my finger to move. It's actually the electrical signal that actually tells your finger to move. So your entire body actually works on electricity and magnetism. And this is actually the side picture of a sun, okay? Our sun, the fact that it emits light, this is something we're going to learn towards almost at the end of the semester. Light itself, all the light around us, is also an effect of electricity. Okay, you may not connect the two together because light doesn't seem like it's an electrical circuit type of thing. It's not a computer, right? But light is also directly a phenomenon due to electricity and magnetism. And we're going to start this journey off with just thinking about what are the things, why does this even exist in the first place, okay? And this is actually, the version we're dealing with is known as a classical theory of it. So we're going to be dealing with things that are moving quite slowly, meaning like maybe a few thousand miles per hour, Okay, that's slow in the physics realm. Okay, and also things that are not at the quantum mechanical level, meaning we're not going to be diving inside the atoms. Okay, we're just going to stay outside the atoms, and we can think about how molecules move, but that's about it. Okay, so anything deeper than that, you actually have to have these a different framework to deal with it called the quantum electrodynamic. And this guy is actually one of my favorite scientists who actually lived in California just like in the 80s. So he passed away before I actually moved to California. But his name is Richard Feynman. He developed these things called Feynman diagram, which actually made it possible for like, silly physicists like myself who are not as good in theoretical work and mathematical work to be able to actually visualize these quantum mechanical processes. But if you're interested in studying this more, it's actually quite a ingenious way to figure out how to teach people like me how to actually do like really complicated, how to at least visualize how the complicated math work, even though if I can't do the complicated math. Okay, right. So let's talk about electric charge. Okay, so in the textbook, okay, the first two sections actually just a bunch of experiments. Okay, and these are like kind of like if you're just reading the textbook, you just kind of have to imagine it. So that's why I want to show you guys this. Okay, so let's say we have two plastic rods. Okay, this one I'm going to go over here to show you. Right. Here's my hat. That's very important. Plastic rods. Okay, at least two until it's kind of charged already. Okay, and if you hang this plastic rod, can everyone see okay? If you can't, just feel free to get up and then just go wherever you need to go. Oops. Oops. Ah. It's much harder to do it in person, of course. Okay. So this is something you can do at home. You just need to hang a little piece of plastic rod on something. Okay. And this is another piece of identical plastic rod. And usually if you're just waving this thing around, nothing happens, right? So that's kind of boring. Okay. But what if I rub this plastic rod with a wool hat that I just wore to go to school this morning? This one. Let's do the one on the, okay. So what I do is, so this is, you guys remember, ever seen this in other classes? They call it what kind of electricity? Anyone? I'm sorry? Static electricity. Because what I'm trying to do is actually deposit charge, well, move charges from either my hat to the rod or the rod to the hat. Okay. Okay. Yeah. So this is experiment 2, where I'm going to rub both plastic rods with my wool hat. Okay. And let's see what happens. See, hopefully this works. Okay. If I move it towards it. So I'm not touching the rod, right? Somehow I'm able to push the rod away from each other, right? I'm actually doing it. Those of you who had General Physics 1, this is also resonance, right? I'm actually pushing, it's like I'm pushing the swing at the right frequency in order to make it move. Okay, you can slow it back down or something. Okay, so that's experiment 2. Okay, there are more experiments that are slightly harder to show. We'll see if that actually shows up, right? Okay, where they have a glass rod rubbed with silk. Unfortunately, I don't have silk. I just have a wool hat. I don't have a silk hat. But what happens is that instead of the plastic rods repelling each other, okay, when you do the same thing with glass on silk instead, they will attract each other, okay? So somehow it's a type of interaction, let's say, right, that can both repel and attract each other. Okay, so I think a lot of you guys probably, I'm being a little bit long-winded about this, right? Because you being grown up in the modern days, you probably know what I'm talking about already, right? So I'm trying to not throw away the punchline, right? Okay. So there's a force that can either attract or repel stuff, okay? That acts at a distance, right? By somehow rubbing just different materials together, okay? There's also a fourth experiment. The force is weaker when it's further apart, okay? The closer you have the force together, the two objects together, the stronger it is, okay? So this is another observation that we should take note of before our next the class on Wednesday. Okay. You can also get these charged rod to pick up little pieces of paper. You guys seen this before, right? And I have little pieces of paper to do this, right? If you charge, I have a glass rod, but unfortunately I don't have a silk thing to do it. And I got some printer paper, right? Tear it up. The little tiny pieces. Actually, I don't need that many, right? Okay, and then get my little rod, rub it, right? And you can actually get them to pick up little pieces of paper somehow, okay? That's weird, right? Because like it makes sense for theirs to be, so I'm gonna give the story away. So I'm somehow charging this rod with either positive charge or negative charge. I'm charging this rod with positive charge or negative charge, right? They're gonna have the same charge, so that's why they repel, right? But I didn't rub these paper at all, right? So somehow they're able to pick them up, even though I didn't rub my hat, right, on the pieces of paper. Okay, so that's odd. Okay, we're gonna have to deal with that and figure out how to explain that. Okay, so similarly, if you have a charged rod that's hanging and you put a neutral rod to it, there's a weaker force, okay, between them. It's not as strong if they're both charged, okay, but there's a weaker force, okay? Somehow, I'm gonna give the keyword away, somehow, right, having charged things around kind of induces another charge in something else, okay? And we're gonna see how that goes, all right? So let's finish up the experiments, okay? So the plastic rods are actually also attracted to my hat. So if I rub this real quick without dropping my pen, those of you who had me last semester knows I drop a lot of things, right? Supposedly, I can actually get them to kind of pull towards each other. Okay, maybe not. This is not a good cloth, unfortunately. Okay, and further along, if you had these two charged rods next to each other, they will attract, right? Putting another object between them, right, between both of them, that has not been rubbed, okay, doesn't cause this any difference. Okay, so those are the 8 different things we're trying to explain with this idea of what's called a charge model. Okay, so this is what we see so far. Okay, the charge model, try to explain all 8 of these phenomenon that we see so far. Okay, so the charge model is that, well, if we apply friction, which means me rubbing those plastic rods, okay, somehow it adds something that we're just going to call it a charge. Okay, it's just a name, right? We could have called it, I don't know, what's a weird name, like, Jamba Juice or something. We added Jamba Juice to our rod, right? Add something called charge to an object, or remove those charge from the object. So you can either put charge on it or remove it. Okay, and this process is called charging. And the longer you rub the thing, the more charge it develops. Okay, all right. There are 2 charges, 2 different kinds of charges. Okay, so in the book, it's nice because they have the glass charge versus the plastic charge. Okay, so me rubbing my hat on the plastic allows the plastic to develop the plastic charge. Unfortunately, I don't have a piece of silk, but if you do the same thing, it'll develop a glass charge. Okay, and there are 2 different charges. Okay, and you're gonna see, why am I being kind of obtuse about this? Okay, so there's 2 different charges. One is called plastic, one is called glass. Okay, we don't know we're not going to assign a sign to it yet, let's say, right? Right. And these forces between these charges, right, can either exert a repulsive force, where you have the same charges, same type of charge, right? But if you have both plastic charges, they will repel each other. Okay. But if you have different types of charge, they will attract each other instead. So glass charge attracts plastic charge, okay? But plastic charges repel each other and glass charges also repel each other. So like charges, repel, opposite charge, attracts, okay? So hopefully this is, you guys are all probably, just saying, so just say the name, right? So, and the forces between these two things, these charges are long range. So that means I don't have to touch it. I didn't have to tap on the little rod in order for the force to be applied, right? So by just kind of getting close to it, you can actually apply these forces, okay? There are also neutral objects, the last thing here, okay? Neutral objects are not neutral because they have no charges on them. The idea is that when let's say a rod is neutral, it has the same number of positive charge as negative charge, okay? Negative, 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 okay? If they have the same number of positive and negative charge, this whole thing is neutral, okay? And we're gonna see how when we rub the plastic with wool, what happens is that you're actually adding negative charge to it, and that's how it charges up. But we're going to see that in a second, okay? So that's the idea of the charge model, okay? That's all we're going to, that's all we can kind of, if we apply this, let's see if we can explain all the stuff that we've been seeing so far, okay? And charge has actually been studied by, hopefully most of you guys knows this guy. His name is Benjamin Franklin. So if you ever have a $100 bill, his name is on it, his face is on it. And he's actually not a president, right? Because a lot of times people say that, money is all the dead presidents. A lot of the people on the bills are actually not presidents, okay? Anyway, so he's actually one of the pioneers who study electricity. And his thing is that, yeah, in the middle, during a lightning storm, what happened is that he flew a kite in the air and put like a key, just some sort of metal, okay? And what happened is that the kite is actually able to pick up the charge from the lightning storm and charges up this key, okay? And, instead of him touching it, he probably has some little kid touch it, right? That's what you do with students, right? Okay, you touch the thing, all right? And, of course, the little student got shocked, right? And what happened is that just by his convention, okay, he's going to call whatever charge that develops on a glass rod when you rub silk on it, because back then I guess a lot of people have silk clothes, right? He called that positive charge, okay? So his interpretation is that when you rub silk on glass, okay, positive charge move from the silk onto the rod, okay? The motions of charge is observed from the perspective of the positive charge moving around, okay? Do any of you guys know why he's wrong already? Anyone know? What charge usually move in with our modern day knowledge? Negative charge moves, okay? But at the time, right, he only had a rod and a silk, so there's no way, he doesn't even know what an atom is, right? Back then there was no atoms, right? There's no molecules, there's no atoms, right? So he had no idea is that that's actually electron, which are the lighter part of the atom. Those are the stuff that moves around as opposed to the protons, which are the heavier part of the material, which does not move around. So in reality, this is false, right? In reality, right, it's actually electrons that got moved from the glass rod to reality, right? It's actually negative charge that's being moved from the glass rod onto the silk, and that's how these material gets charged. Okay. All right. So one thing to notice, let me just do an additional drawing here, right? So let's say we have this little glass rod thing, right? And as I told you, okay, typically materials are neutral, meaning they have the same number of positive charge and negative charges. Let's just do this, right? 6 and 6, right? It's not 6, but it's just to illustrate this, right? So what happened is that when I rub it with the silk cloth, right? So this is the cloth, right? What's happening is that I'm taking this little negative charge, put it over here, take this negative charge, put it over here, right? And maybe do 4 of them, right? 4 of the negative charge and put it over here. Okay. So you think that, well, I mean, so the silk got a net, so this is a net negative charge, right? Or I should say net plastic charge, right? Right. But right, the fact that I remove all these electrons from my glass rod, right, instead of having a neutral, right, now you have too many pluses, right? That's how the glass rod picks up a positive charge. That makes sense? Okay. So you get a net positive charge. And this is very important to understand that when you charge things, right, it's not because, right, there's no positive or no negative charge in it. It's because you just have a slightly more positive, there's more positive charge than there are negative. And that difference is what causes things to be charged up. Okay. Okay. Any questions so far? Yeah, cool. Right. So yeah, so we're going to talk about that because when you charge things up, what happened is that, right, the positive, the glass is going to be attracted to the silk cloth, right? And when they touch each other, that's when the charge can move back to their own place, right? So there is a natural tendency, as you said, for things to be neutral. So when you walk around every day, you tend to, we as human tends to be neutral, but like we don't have carpet here, but like if you're walking around on the carpet on a dry day, right? Sometimes you develop static electricity on yourself and you touch the door, right? Then you get shocked, right? So what happens is that when you're walking around, you develop a charge because you're rubbing your feet against the carpet, right? So you have I actually don't know the sign. You have, let's say, a net negative charge, right? But when you touch the door, what happens is that the door is actually connected to the ground. So you basically, all those electrons will flow from your fingertip into the door. And that's what that shock is. That's why it hurts. A lot of electrons just jumping off the tip of your finger. And that's when it's trying to be, things tends to want to be neutral if possible, because if they're not, there's going to be a force between them, right? Okay. So any other question? That's a good comment and question. All right. So you got 20 minutes left. Okay. So with our modern day knowledge, right, much more knowledge than what Benjamin Franklin had, right? We know about atoms now, right? So in an atom, right, you have a cloud of electrons around it, right? And that cloud of electron is something on the order of 1/10 of a nanometer, okay? Okay, so 0.1 nanometer. Remember, nano means 10 to the minus 9, right? So 0.1 is going to be 0.1 nanometer is 10 to the minus 10, right? Okay. And inside that atom, in the middle, is actually where the positive charges reside. Okay, so this is the nucleus, right? Okay, this is the electron cloud. Okay. Okay. And due to the fact that electrons are much lighter, right, than the nucleus, that's why when you're rubbing things against each other, the electrons are the ones that tends to move around. Okay, it's just a lighter thing to move. Okay, you can move positive charge around. It just takes a lot more force. Okay, especially if you compare the mass of just a single proton to a single electron, and inside the nucleus there's actually multiple protons. Okay, so there's like maybe 10 or 20 of these in there, right? So you can see that the mass of a proton is basically 10 to the minus 27, where the mass of an electron, well, this is a 9, so I should round up, is 10 to the minus 30-ish. Okay, so that means an electron is about 1,000 times lighter than a proton. Okay, and that's why when you have things that are 1,000 times lighter than you, that's the stuff that moves around, right? Okay. Right. So the charge of a proton and the charge of an electron is actually exactly equal and opposite to each other. Okay, and this is going to be a new unit that we're going to introduce to you today called a coulomb. Okay, coulomb is the unit for an electric charge. Okay, this is the SI units for electric charge. Okay, so all the equations that you're going to be using, okay, are going to be relevant to this particular units. There are other units for charges. Okay, so just a reminder from General Physics 1, right? If we want to measure things in distance, the SI unit for that is a meter, right? Which is this line is right here, right? If you want to measure time, right, it's seconds. Okay, if you want to measure mass, it's not grams, it's actually kilograms, right? So you have to convert all your, if I gave you a problem in grams, you have to convert it to kilograms in order to use the mass. Okay, the amount of substance is called mole. So those of you who knows Avogadro's number, 6.022 times 10 to the positive 27, I think, right? Right, that's the, and we actually use Kelvin for temperature, but we haven't really dealt with Kelvin yet. Okay, but instead of using Coulomb, conventionally, we're gonna in the future, you're gonna see this thing called ampere, which is instead of an electric charge, is a current, which is actually the number of Coulomb that moves per second. It's kind of like weird that they use ampere as the SI base unit. So remember, these things are called base units. Okay, but for now, just understand that Coulomb is the SI units for charge. Okay, because we're just going to be dealing with charge, and they're not going to be moving around yet. Okay. Okay. So let's do a quick example. Okay. So if I rub silk on glass and I remove 1 million electrons from the rod, okay, can I figure out how much charge is the rod? Okay. So what I want to do is start my information gathering. Okay, we're going to practice this again, right? I have a glass rod that has equal number of positive and negative charge to begin with, right? But then I rubbed it with some silk and I remove 1 million electrons from it. Okay. Okay. So afterward, right, it has some excess of positive charge by it, right? So what would be the sign of the rod after the removal? Is it going to be positive or negative if I remove 1 million electrons from it? Anyone? Positive, because, right, there's going to be a net charge of positive charge left over, okay? And usually when you say, when we calculate charge, you either use a lowercase q or a capital Q. Typically lowercase means a time dependent one, and we're going to see this in the future, but since we're calculating this without time dependence, let's just use the capital Q, and that's usually a symbol for charge. Okay, so how much charge would there be? I know it's positive, but what's the magnitude? How big is it? How would I calculate that? Anyone have an idea? If I remove 1 million electrons from it, if there's 1 million electrons missing in here, right? How much? What should I account for as the charge? Question? Yeah, you have a comment question? Right, it should be equal and opposite, right? And right. So it should be, right, basically the charge of 1 million, whatever the charge of a single electron is, okay? But the absolute value, right? Because it's positive, right? And I know that the charge of a single electron, right, is, what's up here, right? Negative 1.6 times 10 to 1.602 times 10 to the negative 19. Okay, so negative 1.602 times 10 to the negative 19 in Coulomb. So the short letter for Coulomb is that. Since we know the charge, we know that the charge removed is going to give you the opposite charge of that. So that's why we have a positive here. Okay, so you multiply these two numbers together. The charge on the rod is going to be 1.602 times 10 to the negative 6, 6 minus 19, that's minus 13 Coulomb. Okay. Okay. And we're even going to put it in a different, slightly different unit. 0.1602 times 10 to the, oops, this is going to be 10 to the minus 12. So that's pico Coulomb. Okay. Okay. So you notice that the charge is quite small, right? So, you know, to have charges that have an effect is something on the order of having something that's charged to 10 to the minus 13. It's already a decent amount of charge that you can see in real life. Okay. So there tends, so 1 Coulomb of charge is actually a lot of charge. So that tends to like, we can actually probably see that in a second. Okay. So that's how you figure out, you know, how much charge gets developed on a particular material or not. Okay. One of the weird thing is that this is just a side note. You don't have to write this down. It was always weird to me that electrons and protons have exactly the same charge. And if you are curious why that is, it took me like 20 years of school to learn that. Because I learned about electrons and protons when I was in like 7th or 6th grade, right? Right. And then it's like, and I asked the teacher, why is that? Why are they exactly the same number? And the teacher couldn't answer it, of course. But then when I took the quantum electrodynamics, the thing I mentioned before, there's actually a reason for that. And so if you're curious why, you can go to major in physics and then do like 3 more years of grad school, and then they actually teach you why that's the case. Okay, it has to be that, otherwise the universe would not exist, which is sort of an interesting thing. Okay, so that's a little side note. But the important thing is that, right, when we remove negative charge from a particular object, it becomes positive, right? We can also add in negative charge to an object, okay? Where if we gave a particular atom an extra electron, then it'll become negatively charged, okay? So when you remove an electron, right, it becomes a positive ion. When you add an electron to an atom, it becomes a negative ion. Hopefully that makes sense, right? Because the electrons is carrying the charge. If you remove one, it becomes more positive. If you add one, then you're adding more negative charge to it, okay? So let's do this little quick discussion thing. So unfortunately, this is taken directly from the textbook. So I just want to have you guys think about this, right? In the list of these 5, so just ignore the question up top, okay? So if you have a single proton, a single electron, or 17 protons and 19 electrons, or 1 millionth of each, okay? Or a glass ball that has missing 3 electrons, okay? Which of these 5 things have the most negative charge, okay? All right, so let's give you guys 30 seconds, and then you guys can, I'll ask you guys to raise your hand if you think which one is which, okay? Okay, which one is most negative, okay? We want to get this, the most negative thing. Okay, everyone ready? Is it A? Who thinks it's A? Who thinks it's A? Okay, the most negative thing. Who thinks it's B? Okay, don't be shy if you think it's B. Who thinks it's C? Right? Who thinks it's D? The most negative thing. Who thinks it's E? Okay, so those of you who pick C is correct, right? Right? Because, right, proton is a positive thing, so that's not going to be the most negative thing. One electron is going to be negative, right? But this system in the middle has 2 more electrons than protons. That means the net electric charge here, right? Q, let's use capital Q for this part is actually 2 times whatever the electric charge of an electron is, which is 2 times, oops, I put the negative up here, 1.6 times 10 to the negative 19, right? Coulomb, okay? And that's the most negative you can be, okay? What about number 2? Which one of these systems is the most positive? Okay, let's give it like 10, 15 seconds. Okay. Who thinks it's A? Anyone? What about B? It shouldn't be B, right? Because electron is negative. Could it be C? Could it be most negative and positive at the same time? That's illogical, right? What about D? There's a lot of electrons in D, right? Who thinks it's D? Okay. Who thinks it's E? Okay. So you guys are pretty good at this, okay? Right. So a glass ball, right, with 3 missing electrons means there's going to be 3 extra protons around. Therefore, the charge of this is actually 3 times the charge of a proton, which is, oops, if I can write 3 correctly, 3, right, positive 1.9 times 10 to the negative 19 coulomb, right? So that's how you figure out how much charge are. Okay, so that's a fun little exercise. So one thing to note is that when you rub a material, so if both materials started off neutral, right? If the glass rod picked up, positive 5 protons worth of charge, right? That positive 5 protons worth of charge has to be made up by 5 negative charge that went to the silk rod, the silk cloth, right? Okay, because when you add these 2 charges up here, this one matches with this one matches with this, this one matches with this one matches with this, doesn't match. Originally, the whole system was neutral in the first place, right? But it's the rubbing, what happened is that, and you separate them, right? Now you have a net plus 5 charge here and a net minus charge here. But the whole system, when you add them together, still have a net 0 charge, right? So charges are conserved, meaning you can't just make a charge out of nowhere. It has to. Usually materials are neutral, and then if you take away a negative charge, it becomes more positive. You take away a positive charge, that material becomes more negative, okay? And that charge is still around, okay? It doesn't just disappear into the ether, right? Okay, and that's the idea of charge conservation. Yeah, question? Sorry, can you say louder?
Yeah, it's only talking about removal and addition of electrons, not touching protons, right?
Right. So the quantities so usually the stuff that are mobile is the electrons. Okay. It is possible for you to move the protons around, but that's much harder. So that's why. So you rubbing a piece of rod is not going to move the protons around. Okay. Because remember, they're much heavier, right? Well, especially they're inside there's actually chemical bond that holds them in place. Also, and this detail we don't have to go into, but in electricity and magnetism, the stuff that tends to move around are electrons. Okay, but those of you is there any chemists here? Right. So when you have an aqueous solution, you can have protons that are moving around. Right. Those are the hydrogen atoms that are moving around. But with solid material is always going to be the electrons that are moving around. Okay. All right, so let's wrap up with a short discussion on just talk about these possibility. There are different types of materials out there. There's the 2 types that we're going to talk about are what's considered an insulator and a conductor. And in reality, everything is kind of a little bit of both. Okay, but we're going to classify them that way just so we know how we can deal with a piece of plastic versus a piece of metal. Okay, we're just going to take kind of the extreme of these 2 types of things. Okay. So once again, we're going to look at these little experiments, okay? And I don't think I have time to demonstrate that this time, but next time when maybe tomorrow before we do the group work, where I can show you guys the Van de Graaff machine, okay? So in experiment 9, okay, what happened is that let's say I have a piece of plastic rod, okay? And I rub my little wool hat on it and I charged it, okay? Okay. And if I put it up against a piece of metal ball, okay? What happened is that the charge is actually gonna move from the plastic to the metal somehow. Say, okay, that hopefully that makes sense, right? And it's very easy for charge to move around metal and not very easy for them to move around plastic, okay? And this is why when your electrical outlet has the plastic coating around it, right? So you can hold on to the connector without getting shocked, okay? Okay, and then experiment 10, okay? So there's a rod that's been charged, okay? And then what happened is that I run my finger along that charged rod, okay? Okay, when I do that, so human people are actually okay conductors, okay? So that's why you don't want to stick your finger into the electrical socket, okay? You can actually remove the charge because now the charge moved from the rod to you basically, okay? You can remove charge, okay? So pretend this finger is just a conductor, okay? Okay, what's cool about this, the next one is actually more important, okay? If you have two metal balls, you have a charged rod here and a neutral rod here that's plastic, okay? If you charge up the metal rod by touching the charged plastic to the metal, right? The charge cannot go through the plastic rod to the second metal ball, okay? All right, let's say this is negative charge, right? Okay, this stays neutral, okay? Just put a 0 there, okay? But if you connect the two metal balls with a metal rod instead, okay, the negative charge can actually flow through the metal rod to get to the other side, okay? And this is what we're gonna be calling a conductor, okay? And plastic, we're gonna tend to think of them as insulator, okay? Okay. And that's the main point of this experiment is that there are things in the universe that we can classify as conductor. There are things in the universe that we can classify as insulator, depending on their nuclear structure, okay? And the reason that some things are insulator is because, right, the electrons, so this is very simplified picture, okay? So remember that materials are made of atoms and atoms are made of nucleus and electrons, okay? On insulator, what they call the valence electrons, so those of you who are chemists will know what this means, but just think about valence electrons are the outer shell electrons, okay? They're the stuff that is most accessible to us, okay? The easy to get electrons, okay? In an insulator, those valence electrons are bound so tightly to the nucleus, they cannot move around, okay? So by rubbing, my little wool hat against it, right? This little atom will lose one electron. No, we'll gain one electron. Okay, here's my little plastic wool. If I'm rubbing this back and forth, right, it'll give it an electron, but this electron kind of stays in the same place. It doesn't move around the material, okay, right? But if you have a metal, also known as a conductor, okay, if I do the same experiment where I'm rubbing my little wool thing around it, right, an electron gets deposited here, but they're so loosely bound to each of the nucleus, this electron can move all over the material, okay? So the difference between an insulator and a conductor is that once a charge is there, can that charge move, okay? People call this the mobility of the electrons, okay? And that's what I want to think about when we're demonstrating how we can use the combination of insulator and conductor in order to make, laptops and black batteries and lights and stuff like that. Okay, so I'm going to wrap up today here, and then and I'll do the demonstration for you guys with that on tomorrow when we do the discussion also. Okay.